Now next topic, that is LC oscillations. See, suppose we have a capacitor and inductor, and suppose capacitor and inductor are connected with each other as shown in this circuit through a key. Now initially the key is open, and at time t equal to 0, suppose the capacitor is fully charged. Now here we are considering the idealistic situation. There is no dissipation of energy in the form of heat in this particular circuit. Okay, by considering this thing, we are considering this circuit. At time t equal to 0, suppose the capacitor is fully charged, and charge on the capacitor, that is maximum one, and that is Q equal to Qm. Okay, now we switch on the circuit. As soon as we switch on the circuit, then charge will flow in the circuit, capacitor start discharging, and current will be constituted in the circuit. Suppose at a particular instant t, charge on the capacitor is Q and current in the circuit, that is I. So potential difference across two plates of the capacitor, that is Q by C. Potential difference across inductor, that is minus L di by dt. So we can write as per Kirchhoff's second rule, Q by C minus L di by dt, that is equal to 0. So here we have I, that is dq by dt, but we take I, that is minus dq by dt, because here with time the charge is decreasing one. Clear? So rate of change of charge, that is decreasing one. Therefore here we introduce one negative sign. So now if I is replaced by minus dq by dt, then we will get the equation L d2q by dt2 plus q by c, that is equal to 0. Okay. Now we can rewrite this equation as d2q by dt2 plus 1 upon LC into q, that is equal to 0. Now see, the form of this differential equation is exactly like the differential equation of pure simple harmonic motion, means intrinsic oscillations, that is d2x by dt2 plus omega 0 square x equal to 0. Now by comparing these two equations, we can say this constant omega 0 square, that is 1 upon LC. Now in standard 11th, when we discussed this differential equation of simple harmonic motion, we derived its solution, that is y equal to a cos omega t plus phi. So here we can consider the solution of this differential equation of charge as q equal to qm cos omega t plus phi. Now at time t equal to 0, q equal to qm, that we discussed very first. At time t equal to 0, capacitor is fully charged, so that is the maximum charge on the capacitor. So in this equation, if we substitute t equal to 0 here and q equal to qm, then we will get cos phi, that is equal to 1. So phi, that is equal to 0. Now if we substitute phi equal to 0 in the solution of the differential equation q equal to qm cos omega t plus phi, then if we substitute phi equal to 0, we will get q equal to qm cos omega 0 t. Now I, that is the differentiation of this one, dq by dt with negative sign. So that will be I qm omega 0 sine omega 0 t. So I that is equal to Im sine omega 0 t, where Im that is qm into omega 0. Now we have the equation of charge at any time t as well as the current at any time t. Now let's think about the energy. Okay, so at any instant t, the energy in the form of electric field, that is q square by 2c, but charge at any instant, that is qm cos omega 0 t. So we can write here qm square upon 2c cos square omega t. Similarly, at the same instant, energy in the form of magnetic field, that is um equal to half li square, that is half l, I that is im sine omega t, so im square sine square omega t. Okay, now here you can write um that is half l. Now im that is qm omega 0, so qm square omega 0 square sine square omega t. Now omega 0 square, that is 1 upon LC, that we discussed on the previous page. See here, by comparing these two differential equations, we mentioned this thing omega 0 square, that is 1 upon LC. So here if we substitute 1 upon LC, then LL will be cancelled. So we will get energy in the form of magnetic field, that is qm square by 2c sine square omega t. So now resultantly we are getting energy in the form of electric field qm square by 2c cos square omega t, and in the form of magnetic field, that is qm square by 2c sine square omega t. Clear? And now with time t, here as per this equation of charge and current, see, current and charge are continuously changing with periodic functions. Means periodically charge or the current is changing. So we can say this one is the oscillatory circuit, because charge is oscillating, increasing, decreasing, increasing, decreasing, increasing, decreasing, like that. And energy also here changing continuously from electric energy to magnetic energy to electric energy. Clear? And in doubt up to this one, 0. So at time t equal to 0, we can say the total energy that is in the form of electric field and energy in the form of magnetic field, or we can say magnetic energy, that is 0. Then at time t equal to t by 4. So here if we take omega, that is 2 pi by t, and substitute t equal to t by 4, then this will turn to pi by 2. So electric energy will be 0 and magnetic energy, that will be maximum 1 qm square by 2c, or we can say that is half L Im square. Then at time t equal to capital T by 2. So again here if we substitute t equal to t by 2 by taking omega equal to 2 pi by t, you will get the total energy that is in the form of electric energy, and at that time magnetic energy will be 0. Again at 3t by 4, electric energy will be 0 and the total energy will be in the form of magnetic energy. And at time t equal to capital T, again we will get the total energy in the form of electrical energy. Okay. Now here if we take more less time interval here, t equal to 0 and t equal to t by 4. Suppose here we consider t equal to t by 8. So if we substitute here small t, that is t by 8, 2 pi by t. So we will get here this one pi by 4, and cos square pi by 4, that is 1 by 2. This will be also 1 by 2. So in that particular case, we will get the total energy that will be half in the form of electric energy, half in the form of magnetic energy. So in this way, the oscillations will be obtained. Here, the idealistic situation is obtained, means there is no resistance of the inductor is considered. It implies that the dissipation of energy in the form of heat, that is zero. Otherwise, in realistic, there is some resistance, and due to that, the dissipation of energy in the form of heat is always there, means the total energy that will be slowly decreasing one, and finally your oscillations of charge will vanish. Clear? And suppose here we consider the idealistic situation, then also the decrease in energy takes place, because oscillating charge that emit the electromagnetic wave, and electromagnetic wave, that is nothing but energy. So oscillating charge, when emit the energy in the form of electromagnetic waves, then also the energy associated with this LC oscillatory circuit decreases, right? So here always the energy decrease takes place, and oscillations will be damped oscillations. See example 7.11. So that in the free oscillations of an LC circuit, the sum of the energies stored in the capacitor in the inductor is constant in time. Now see here, with this particular derivation of the energy at any instant t, the energy in the form of electric field, that is qm square by 2c cos square omega t, and at any instant t, energy stored in the form of magnetic field, that is qm square by 2c sin square omega t. So now at any instant, the total energy, that is ue plus um. So if we take the summation of these two, then qm square by 2c, that is common. So into bracket cos square omega t plus sin square omega t, but that is equal to 1. And therefore, the total energy that will be qm square by 2c, and that is constant 1. That is constant 1. Clear to all of you? So that particular example 7.11 is discussed with this theory of LC oscillations.